Assalamualaikum warahmatullahi wabarakatuh and good day everyone. Today we will continue our lecture about a new chapter which is chapter 5, and we will discuss about numerical integration here. As you know, in the previous lecture we have discussed about numerical differentiation, and the integration is the antiderivative. So now we will discuss about numerical integration, and this is a little bit introduction. And as you know, this method involve in approximation of definite integral here. If you have definite integral from a to b of any kind of function, and we want to integrate with respect to x, for example, but we don't know what kind of fx here. Fx here, maybe it is complicated, or maybe it is very difficult to evaluate analytically by using any approach that you already know. For example, by using substitution by part, and then the numerical integration is needed. This one, the function to be integrated is complicated, and therefore it is difficult to integrate. And sometimes from the experiment we also can have a tabulated function, meaning that at certain point that function, or at certain point we have that kind of value, and so that we cannot integrate analytically by using substitution and so on. And in this case also we need to use numerical integration. And as you know also, the integration actually it is a method to find the area under the graph. So for example, like in this picture, let's say this y, this is the function y is equal to fx, that is limit from a to b. Here we have the left limit and right limit a to b, and then we want to know what is the area under this graph, or what is the area of this graph. And maybe we don't know what is the function fx here, or if we know that the function here maybe is too complicated to evaluate, and so that we need a numerical method to find the area. So in this chapter we will discuss three technique or three approach in solving the integration numerically. And the first one we call trapezoidal rule, and the second one is 1/3 Simpson rule, and the last one is Gaussian quadrature. So here the quadrature here, actually it is other name about integration. So sometimes integration also is called quadrature. And under this one we will discuss about 2 point, and I think, if I'm not mistaken, 3 point, but never mind, we will discuss one by one. So we will go with the trapezoidal rule first. So, and here as you can read, it is the simplest numerical integration that use polynomial of order 1. And here is some explanation you already know in the interpolation. If we have a tabulated function, and then we can approximate what is the kind of polynomial of degree n that we want, so that here we can get, since the trapezoidal rule is the simplest numerical integration that use polynomial of degree 1, so that by using Newton forward difference, this is the formula of order 1, polynomial of order 1. And then after that, let's say it is our function f(x), and from a to b, the limit of our integration, and then you just substitute, and what we will have is this formula. And this formula is called area of trapezium. So basically the trapezium, it is something like this. The shape, it is like that. Okay, so this is one way how to show how to solve that the area of or trapezoidal rule by using Newton forward. So but we also, in the previous lecture, I think in chapter 3, we also know about another method to interpolate our polynomial. So let's say that we want to use Lagrange interpolation. And of course we need to use order 1. This is other alternative that I want to show it to you. So as you remember that the Lagrange interpolation, the Lagrange interpolation of degree 1 is given by P1x is equal to L0 x F0 x plus L1 x F1 x, where your L1 or Li is equal to the multiplication of j equal to 0 to n, where your j cannot be 1, of x minus x j divided by xi minus xj. So in other words, this is also a little bit revision for you. And this is, so here we need to find our L0. And if you just substitute by using all the formula, what you will get here is x minus x1 divided by x0 minus x1 F0 x plus x minus x0 divided by x1 minus x0 multiplied by f1x. And let's say now we want to evaluate the integral from a to b, where your a is now is your x0 and b now is your x1 fx dx. And so we know that our x1 is equal to b, so you just substitute x minus b divided by a minus b, and here is fa plus x minus a divided by b minus a f b. Okay, and then what you can do is, after that, you just need to substitute to your fx here. So the integration from a to b of fx dx, also approximately a to b of your P1x, and your P1x is x minus b divided by a minus b multiplied by fa plus x minus a divided by b minus a fb, then all of these integrate with respect to x. And now you can evaluate. You have fa divided by a minus b from the first term because it is a constant. Now when you integrate x minus b here, what you will get is x minus b square divided by 2, and the lower limit is a, upper limit is b. While for the second term, what you will get is fb divided by b minus a multiplied by x minus a square divided by 2a to b. And then the next step is you need to substitute the upper limit minus lower limit into x because we integrate with respect to x. So for here, what we will get is fa divided by a minus b. And then here b minus b square divided by 2 minus a minus b square divided by 2. While for the second term, fb divided by b minus a, and then b minus a square divided by 2 minus 0 because a minus a is 0, and here also is 0. And then what you will get is negative fa divided by a minus b multiplied by a minus b square divided by 2 plus fb divided by b minus a square divided by 2. And then you can cancel the same term, and then what you will get is, so let's say we bring out fa, and also no, we bring out a minus b divided by 2 because this one, if you multiply minus with the a minus b, what you will get is b minus a divided by 2 for both, and your fa now becomes positive, and your fb plus fb. And then we know that b minus a, actually it is h. We can write h divided by 2 fa plus fb, where h is equal to b minus a. Alright, so this is what we call trapezium rule or trapezoidal rule. It is same, h divided by 2 fa plus fb. So now you have you can do by using either Lagrange interpolation or to evaluate our fx, or you can use Newton forward or Newton backward. And then this is only for one trapezium. If you still remember, what we trying to do is from x0 to x1 fx dx, this one. So now let's say what we want to do is to find the area under the graph. So the first step actually, or the basic idea, by using the formula of trapezoidal rule, what we do is we can divide our area under the function, our function, into sub interval, into many sub intervals. So now let's say we divide our area under the function under the graph into 6 sub interval. Here we have 6 sub interval, and then after that, for each interval we want to know, or we can evaluate the area for each sub interval. So we just use the formula that we just derived just now, and then you can get area A1 here plus area A2 plus A3, A4, A5 and A6, and then you just substitute. So this is from the first one, the second one, the third one, fourth, fifth and sixth, and then after all you just simplify, and this is what you will get if you have 6 sub interval. So you have one term for f0 and also f6, and the rest you must multiply by 2, because here you have half f1 plus half f1, half f2 plus half f2 here, half f3 here plus half f3, so that you will get this formula. Or in general with n sub interval, you will get this formula. The first and the last sub interval for that function, you don't need to do anything, but for the inside interval you need to multiply by 2. And as you can read, the composite formula is not given in the list of formula in your exam, so that you must know a little bit how to derive, or maybe you need to memorize. What you only be given in your final exam is from A to B, and then fx dx is equal to h over 2 multiplied by fa plus fb, or the formula for integration for one interval. And then if you have want to use for how many interval, you need to memorize a little bit the formula in general form. Okay, so now we want to apply the formula into the example here. So for the first example here, evaluate from 1 to 2 for the function x ln x dx for n is equal to 4. So you just apply. So for this one, you will get from 1 to 2. It is same. Maybe I no need to write. So maybe it approximate h over 2 multiplied by f0 plus f4, because it is a first left n and also right n, and then for the inside, in the middle is f1 plus f2 plus f3, because your n is 4. And you also can calculate what is your h. Your h is equal to 2 minus 1 divided by 4. Your b minus a divided by n, and then you will get your h is equal to 0.25. And your fx is here, x ln x. Your fx is equal to x ln x, and fx0 also is equal to f0 also is equal to x0 ln x0, and so on, f1, f2, f3 and also f4. So here we need a kind of table. It is easy for us to see where you do something wrong in your exercise or in your assignment, or the most important thing in your final exam. So here we need a table like this. Here is your xi, and then here is your fi is equal to xi ln xi. So now let's say because you have 4 subinterval, 0, 1, 2, 3, and 4, and then your x start from 1 to 2 here, you see, 1 to 2. So that, and your h, your space between point is not 0.25, so here is 1.25, 1.5, 1.75, and here is 2.0. And your fi, you just need to use your calculator, you substitute. So let's say your equation y is equal to x ln x, and then you just calculate. When your x is equal to 1, of course you will get 0, because ln 1 is 0. And if you put your value of x is 1.25, you will get 0.2789. And then when x is equal to 1.5, you will get 0.6082. When x equal to 1.75, 0.9793. And when x equal to 2, you will get 1.3863. So here we try to use 4 decimal places. Okay, and then after that, so that if we want to apply to the formula here that we have, so you just, so meaning that from the integration from 1 to 2 of x ln x of dx, approximately h over 2, 0.25 divided by 2 multiply by f naught plus f4, 0 plus 1.3863, you'll get 1.3863, and the rest you must multiply by 2. The summation of the rest, f1 plus f2 plus f3. So you just write 0.2789 plus 0.6082 plus 0.9793. And then you can calculate, and if you do that, you will get the answer is 0.6399. Okay, this is how one example how we use trapezoidal rule to evaluate our integral. And then for the second example, you have fx is equal to 2 upon x squared plus 4 with subinterval 6 n equal to 6. And then it is the same step where for b, if you do that, you will get your h is equal to 2 minus 0 divided by 6. It is 1/3. Okay, this is your h. And then after that, you just need to calculate what is the value of your fi and so on. And then you just substitute into the formula. And of course, for this b example, the integration from 0 to 2, 2 divided by x squared plus 4 dx, it is approximately h, it is 1 over h divided by 2, you will get 1 over 6, and then multiply by f0 plus f6 plus 2 multiply by f1, this is f6 plus f2 plus f3 plus f4 plus f5. And then from the table that you do, exactly like this one, but up to 6, up to I equal to 6, and then the answer for this one is you will get approximately 0.7842. This is your answer when you evaluate this function numerically.